Hi. So my name is Achintya, and today we'll be presenting our work on causal discovery in financial markets. This is work done by colleagues, Agathe, who is a PhD student at Stevens, who did this work with us when she was interning in the Bloomberg Quant Research Group, again, with me and Mohammad. The project started with exploring what causal discovery can tell us about financial data. And as we looked deeper into these algorithms, a consistent theme is that the reliability of these algorithms rests upon the assumptions. And to this end, we spent more time. Oh, really? Sorry about that. It says they can't see it anymore, the screen. How about now?
Ask if they can see.
Can you see our screen?
Yep.
Sorry about that. Does
You're
this
back on.
Yeah, we see it.
Cool. Awesome. Sorry about that.
I see it.
Okay, sorry, I saw a message in the chat for that. Okay. Yeah, and so to this end about the assumptions, we developed a new algorithm called CD knots that we think is more compatible with financial data, specifically for properties such as nonlinearity, non-Gaussianity, contemporaneous effects, and possibly most importantly, non-stationarity. So generally, our presentation will be structured this way. We'll first give a quick intro to causal discovery, go into detail what is CD knots, which is the algorithm we developed, some experiments on synthetic data, and then finally it on financial data. So what is causal discovery? Simply put, is just trying to find cause and effect relationships from data. And importantly, the assumption here is that this isn't randomized controlled trials. This is not interventional data. This is just data naturally happening in the world. And the idea is that if we have something like this, some possible use cases could be investment strategies where there is a belief that investing in causal relationships is more robust. Policy analysis, was the causal effect of a policy? What will be the causal effect of a policy? And then possibly even interpretability in machine learning, where it is also believed that interpretation done with a causal language is more understandable to a human. But again, we're going to focus more on causal discovery. And so an important thing to always do when running algorithms that are trying to learn something from data is asking the question, how do we evaluate our algorithm? How do we validate it, right? And unlike in predictive modeling, we don't have ground truth, right? We don't have, at least in finance, we don't have many examples of observational data and a ground truth graph with it that we can do an out-of-sample evaluation on. Instead, what could we do? We could do interventional studies, which again, in finance, a little bit difficult. So what kind of remains is the assumptions, evaluating the reliability and the realism of the assumptions. For simplicity, we bucket these assumptions into 3 different types. There's what we call objective assumptions. These are assumptions that are statistically testable. Is it fair? Does the data say there's a linear relationship? Does the data say it's stationary? There's other assumptions we call algorithmic assumptions. You can think of these almost like the parameters of your algorithm. So significance level of the conditional independence test, the type of conditional independence test, right? These, while there is general guidelines on how to set these, to a large extent, it's hard to justify one over another. And so we believe it's important to test the robustness of your conclusions to these. And then finally, there's what we call subjective assumptions, assumptions that require domain expertise to evaluate, such as no missing confounders or faithfulness. Many of the terms we're using here, we will define soon in the next set of slides, but just to kind of set up, the whole idea is that a consistent theme that's going to arise for the rest of the presentation is going to be this, assumptions. What are the assumptions? How realistic are they? And when they are testable, that we test them. Okay, so now going to more about causal discovery, I'm going to pass it over to Mohammad.
So yeah, I'm going to give you a quick intro about the causal discovery and the challenges that we are facing. So essentially, the dependencies that we observe in the data can come from one of these 4 type of scenarios. So here I'm ignoring the random effects that we may see in a small sample. So assuming we don't have those kind of conditions. So the dependency we observe between X and Y can be the reason can be because X causing Y directly, or it can be even indirectly through another variable that we call a mediator. Similarly, Y can be a cause of X and directly or indirectly through other variables. So we can see the association between X and Y if they share a common cause. That cause, we see some sort of relationship between them. And lastly, the final case is actually the most interesting one. We can induce this relationship between two even seemingly independent variables by conditioning on their common effects. And to make it more clear, let me give you an example. Imagine X and Y in this case are like the spouse's income in a household. So spouse's income is normally independent. However, when we condition on total household income, they become suddenly negatively correlated. So these two had nothing to do with each other, but the fact that the condition on the total income induce some kind of negative correlation between them. So now the question is, how are we supposed to find the real causal connections? How to distinguish between non-causal one and causal one in observational data? It turns out this is a very difficult problem, actually. For example, if you look at these graphs on the left in this chart, you can see that if you generate data from any of these three graphs, the dependencies and we observing the data are exactly similar. So we're going to observe X, Y, Z are dependent to each other. There is one of these variable if that we condition on, in this case, is the Z variable. The other two become independent, but there's no way for us to distinguish if this Z variable, condition variable, is a common cause of the X and Y, the other two, or it's just a mediator. So no way for us to tell just from the data how these guys are structured. However, the graph on the right one is the one that we can distinguish. So if we have two independent variable and we condition on some other variable and we observe that they become dependent, we can say that two other variables are the common cause of this variable. So we call this case the collider case, and because of the shape of this graph also is known as a V structure. So in general cases, when we deal with the much bigger networks, we need to come up with some kind of algorithm that can efficiently handle these cases for us. So there are two sets of class for this. One group of these algorithms is a score-based approach. Essentially what they do, they come up with some kind of a score that to evaluate how well the graph that they discovered fits the data. And the good thing about this method is that they are normally able to handle larger graphs. However, the assumptions about the score functions is very hard to evaluate. If we see a link in this graph, it's really hard to say where it came from and what's the origin of it. So kind of opaque and less interpretable in that sense. So the other class of methods that are actually constraint-based approach, and our method CDNOS belongs to this class, can help us with solving some of those issues. Essentially, the way these algos work is that they start from fully connected graph. They assume any two variables are connected, and they remove the link only and only if they can explain away the dependencies given other variables in the graph. So this makes them very interpretable. We can say why a link is there or why a link is not between two variables, because it could have been explained by other variables. The con, however, is that computationally they can become very expensive when we are dealing with very large graphs. Here I show you on a toy example how these two classes of algorithms work. Imagine we have this var-type process that we generate this 6x series and with the samples of around 300 samples in this case. And our task is that to recover the true causal structure. Talking about the true causal structure, we can show it either as a full time series graph, you can see in the bottom left, or we can also represent it as a summary version. You can see it on bottom right. Essentially, the summary graph shows for each node or time series, we have a node. And if there is a link between two nodes, means they are causally dependent. And we put the lag dependencies, can be one or more, on the middle of this edge. So this generating process on the top can be explained, can be shown in a causal way in this summary graph. Now let's see the results of our algorithm and score-based algorithms. So in this graph, the red links, the black links are essentially the correct ones, and the orange ones are the ones that they are false positive, and they do not exist in the real causal graph that you can see on the left. as you can see, our algorithm has been able to recover almost all edges except the one from X2 to X5, which had a very low correlation. And considering that we didn't have many data, the test could not recover it from this test. And if we look at the spur-based function, you can see we are dealing with a lot of spurious links, especially in the case of var, we can see almost half of the links are spurious. However, it has been able to recover the true graph. Some of this, but the precision is quite low. So finally, discussing about what kind of causal discovery is appropriate for financial data, we need to remember that in finance and similar fields, we are dealing with kind of dynamic and very complex processes. We may be dealing with kind of chaotic state-dependent time series. We may be dealing with regime change, with extreme values, and all other kind of situation that it may arise. So any model that's gonna help us with causal discovery in finance is supposed to be able at least to take care of nonlinearity, non-Gaussianity, the lag dynamics in the form of, lags and contemporaneous effect, and most importantly, non-stationarity. And our algorithm is the only one that can handle all these situations. So now we are done with the introduction part, and Agathe is going to tell you what actually CD node is, and we're going to see more details about Agathe.
Okay, so how does our algorithm CD nodes work? CD nodes is this constraint-based causal discovery from non-stationary time series data. And I'm going to walk you through an example to get a better understanding of the algorithm. So let's say that we start from 4 time series, A, B, C, and D, and then we want to consider their first lag as well. So all in all, in this graph, we are looking at 8 nodes, and we start from a fully connected graph because this is a PC-based algorithm. So every link between each pair of nodes are drawn out. So in the first stage, we want to bring this non-stationarity into play. So we add a node, a time index node called U, which you can think about it as time. What we expect here is that if a time series is non-stationary, its corresponding node would have a link through U. One assumption that we got here is that we don't have any unobserved confounders. However, if a confounder can be written as a smooth function of the time, then it would be captured by the time index node U. So in the second stage, we start pruning the network so that we remove the links based on conditional independent tests, like the kernel-based one. So the intuition behind this is that if the link remains, meaning that 2 variables, 2 nodes are connected to one another, it means that there is no set that we can condition on that would make those 2 nodes independent. Put it in other words, if 2 nodes are independent from one another, meaning there's no link in between them, their dependency could be explained through the other variables. In here, we got set of assumptions. So the first one is the fundamental assumption of faithfulness. This basically means the structure that we see in the network is the same as we would see in the data. We have consistency. This means that the structure that we see at time t is the same as t minus 1. So if there is a link today, it would have been there yesterday as well. We have the pseudo-sufficiency. This is reiterating the thing that there are no latent confounders. And the last one, we got randomness. So the CI tests, they form this test statistic. And when they calculate their p-values, they have this randomness assumption within themselves. So from stage 3, we start orienting the edges. So there are a set of edges that we can orient upfront. The first one is arrow of time. So we believe that causes happen before effects. Hence, if there is a link between nodes at time t minus 1 and t, this is going to go from t minus 1 to t. The second one is if the links that are going from the time index node U. So we think about U as time, and time is what is making the other nodes non-stationary. So if there is a link between the U and any other node, then it would be pointing outwards, because it is also counterintuitive to think that any other time series is going to cause time. The third set of links that we can orient is basically the structures like the colliders, or also known as B structures. So that is what we have in here between B, C, and D at time t. So basically it means if we look into B and C and we condition on its parents AT and AT minus 1, they're independent. But when we add DT to the conditional set, they suddenly become dependent. And this is the essence of the colliders. When added to the conditional set, two independent variables, they become dependent to one another. So in here, you can see that there might be some edges left that are yet not oriented. So the edges between A and B at time t and t minus 1. So at stage 4, we start orienting this. We try to orient this. And these are the links between two nodes that are non-stationary themselves. And as you can see, A and B, both of them, they have links through U. So the assumption that we got here is that the causal distribution changes, they're independent from one another. So if you think about the distributions as modules, if one changes, it is not going to change the other one. It's not going to affect it. And for this, we built this measure. This is a dependency measure, which is a combination of gram matrices and NHSIC. And what it does is that it tests for the statistical independence of the conditional distribution and the marginal distribution, and then tries to orient the edge. So let's say if we look into the A and B, if this dependency measure for the conditional distribution of B given A and the marginal distribution of A is less than this same measure for the same distribution, except now the variables are flipped, then we would know that A is the cause and B is the effect. Hence, we will orient the edge from A to B both at time t minus 1 and t. One thing to note here is that this assumption is by far the strongest assumption that we got in our algorithm. But interestingly enough, it doesn't come up in our case studies, meaning that we are able to orient all these non-stationary, the edges between non-stationary nodes in the prior stage. One thing to also highlight is the consistency that we keep. So this consistency assumption, we keep it all through these stages. As you can see, the structure, both in the skeleton and also in the orientation, is the same at both of the times. And if we had more lags, these cross-time orientations would have also been consistent. So now we have an idea about how this algorithm works. And Mohammad is going to walk us through some simulations that we did using this algorithm.
Thank you. So yeah, we performed we created a large set of data to study the behavior of city nuts. So specifically, we create 350 graphs ranging from 3 nodes all the way to 15 nodes. The connections in this graph between the edges can be linear, but they are mostly non-linear in terms of quadratic, exponential, or even sine system. And for each of these 350 graphs, we generate different random data. So ranging from 50 all the way to 1,000 samples. So it kind of represents low data regime when we have plenty of data. And the lag connections are also random with the max capped at 5. For the conditional independent tests that we study, we have 3 classes of tests here. We have hardcore, which is linear test, partial correlation. We have K-seed and RPAD, which are nonlinear kernel-based case, and we have a CMI-KNN, which is a conditional mutual information-based, which is for nonlinear cases. So here we can see a comparison between different CI tests in different data regimes. The metric that here I use to compare the performance is FS score, which is essentially precision times recall divided by precision average precision recall. So when it's 1 means that we have recovered the true graph without any spurious link, and when it's 0 means that we could not find any correct link at all. So one observation is that in the low data regime, this nonlinear kernel, especially in larger graphs, suffer a lot. They are struggling to get a good FS score, and it's expected. Very large graphs, very few samples. However, one interesting pattern is that the parkour doing much better in this nonlinear graphs than the linear, than the nonlinear, sorry. And as we get more data, the FS score improves drastically. So at around 500 and more, the difference between all these nonlinear tests is almost negligible. And as you see, they are doing much better than parkour. And if you look at the performance more closely, CMYKNN and RCOD are the best performance, followed by KSEED and parkour. The performance of RCOD, CMYKNN, however, comes at a steep cost. Like here, you can see the computation times of this test. Partial correlation is almost costless, scale very well with the size of the problem. The CMYKNN actually is like 10,000 times slower than parkour. KSEED and RCOD are much faster and around like 1,000 times faster than CMYKNN. So the choice of the test really depends on the computational resource that is available and how big is our data sets. We can also see the number of tests that we need to do for different network size in average. As you can see, this number increases very rapidly as the network increases in size. We also try to see what level of alpha is the best for our test. And this is the only hyperparameter that our algorithm has. From our observation, we can tell that when we have few data, it is better to set the alpha around 0.05, 0.05, or even higher. They have a better performance. But as we get more data, let's say 300 and even more, it is better to have a more restrictive alpha. So it helps with decreasing the number of false positive links that we may get. So here we recommend getting like something 0.01 or even a small. And finally, we are comparing here the performance of our tests with other algorithms, like here is PCNCI, which is another comparable algorithm. Our results are in blue. You can see that our algo CDNAS consistently outperform the PCNCI, which is quite promising. Now that we know how this algo works, how it reacts for different data regimes, Achintya is going to walk you through some financial case studies.
Cool. Right. So basically, I'm going to walk you through 2 of our case studies. That's in our paper. There's a third in there if you on economic data if you're curious. So for the first one, we look at the Fama-French factors and also Apple's daily returns. And basically, what we're doing, is looking at the data from beginning of 2000 to the end of 2022. So looking at the results, this is having run CD-nauts on that data. On the right, we have a full time series graph. We have all the lag relationships as well as all the contemporaneous. However, as you can kind of see, all the contemporaneous are kind of smushed together in that visual, which is why on the left, we also just separately plot out just the contemporaneous so we can kind of look at them separately. The coloring scheme, I think, is important as well. This is not based off the strength of the relationship. It's based off the max p-value across the different tests run on those pair of nodes. The reason we did this is because, as Mohammad was talking about, when we have a lot of data, our synthetic data experiments suggested that a better threshold to use might be 0.01. However, since it does seem that the literature often uses 0.05, what we decided made sense is let's run it with 0.05. But with this coloring, you can then see the sensitivity of this graph of the result of the algorithm basically to this hyperparameter. Had we lowered it to the 0.01 level, the red edges, the black edges would be removed. Okay, so what results do we see here? So the first thing we see is that the T node, this is the non-stationary node, points to apples returns. So in essence, it's saying that apples returns can't be fully explained away by its factors, by the factors. And on the slide, the way we phrase that is that the factor exposures of apple are non-stationary. The reason we take this interpretation is because given some plots in our paper, we also ran this on shorter time intervals, i.e. 8 years instead of full 2 decades. And in smaller time ranges of the 7 to 8 years, the T node doesn't point to apples returns, which means in those shorter term experiments, apples returns become stationary once you condition on the Fama-French factors. But the fact that it pops out when it's more than 2 decades of data implies to us that basically there's some level of non-stationarity in the factor exposures, which, again, given 2 decades of data, to be expected. Another thing that is interesting is most of the lag relationships in this graph have a high p-value, which at least suggests that had we set the threshold to the threshold that we found to be a little bit more, at least useful in the synthetic data, all those edges would have been removed. And so this doesn't mean that there isn't a dependency through time, right? There is still this non-stationary node T, which can induce dependency through time. And the fact that the graph looks like this, at least we believe, is intuitive. The reason is because of volatility clustering. Volatility clustering basically can be viewed as there is some latent variable underneath it all that there's a latent variable underneath it all that has its own process. And so because of that, and so if you imagine that graphical model, and because volatility isn't one of these variables, basically the T node plays that role. Okay, so what about the assumptions that we use that at least we say are important for finance or lack of? We don't talk about how we did this test in this presentation, but again, it's in the paper. We test if SMB is nonlinear with respect to its parents, and we did find this, that it basically, assuming linearity is not consistent with the data, nor is actually assuming time-varying linear consistent with the data as well. Further, the fact that the T node points to other variables tells us that consistently the null hypothesis of stationarity was consistently rejected, which at least means from the data, it's not fair to assume stationarity. But what would have happened had we run this algorithm with that assumption? So over here, we just showing the contemporaneous plots. Left is with non-stationarity, right without it. We see that we almost get the exact same graph. Visually, this is a little bit hard to see because the T node like points and kind of clutters it up. But if you walk through each edge at a time, they're all basically there except the one from SMB to CMA. What's more interesting, though, is in the lag relationships case. In the lag relationships case, most of them are now statistically significant, right? Why? Because there is a dependency through time. And if it can't attribute it, and since there's no non-stationarity node for it to attribute it to, it has to put it this way. And so what does this mean? It means if you had assumed stationarity, you would lead to spurious causal relationships. Mohammad is actually going to talk about one other use case finding we had when looking at this data.
Yeah. So recently, I saw this causal example. I mean, it's a hypothetical causal graph, I better call it. So in one publication in which they show that momentum might be a driver of HML. So I was wondering if this is really the case. Since we had this Fama-French data, I decided just give it a try, add momentum to Fama-French factors, and see if there is any relationship as we see. So here in the middle graph, you can see the correlation between momentum and other Fama-French factors. As you can see, momentum and CMA both have a high correlation with HML. However, the correlation between CMA and momentum is quite small. If we draw the correlation between these two variables based on different levels of quantiles of the HML, an interesting pattern emerges. You can see in a smaller quantiles of HML, we have a very high correlation. So two independent variables suddenly became very dependent condition on the levels of HML. So this kind of hints us there may be some collider case in play in this case. So to do it more properly, I run CDNAS on this data. The way I do it, I do through bootstrapping approach. So I can also get a feeling of persistency of the link over time. So the way I do it is like this. I select a small period of time, let's say here 6-7 years, I assume I do it, and randomly select this period, learn a graph on it, Then I randomly select another date, 6 years period, and learn another graph on it. I keep doing it, maybe hundreds of times. At the end, I start averaging this graph. So I see how often a link has been appeared in this learned graph. So this kind of gives us a feel of persistency because these graphs have been learned in different market conditions. So if a link appears to be always there, means that it's most probably an important one. So
5 minutes to wrap it up, okay?
sure, thanks. So as you can see here, the link from momentum and CMA to HML are the most persistent one, and they have been appeared in more than 84% of the time. For CMA, it's almost 90%. So this finding kind of give us a better confidence that the momentum might be really a driver of HML, both momentum and CMA. So back to you, Rashid.
Cool. So another case study that we did was with company financials and stock returns. Again, there's an economic data one that's in our paper if you want to check that one out. Over here, what we do is we look at the relationship between the price to book ratio and the returns of financial sector companies in the S&P 500. Because later we do we do a bit of a back test. We try to ensure everything's point in time. So this is the S&P 500 point in time members. This is the price to book ratio known at that specific end of quarter. So this is just the contemporaneous part of that graph, mostly so I can walk you through every variable. So going from the left, we have the security ID. The idea here is that we're not trying to do the causal relationship amongst the securities. We're simply grabbing multiple stocks together to pull the data together to help increase the statistical significance of the tests. And so, but we still add this node just so that our algorithm has the ability to make stock-specific decisions if it chooses to. Over here, we have log price to book ratio. The log is going to be for the normalization that comes soon, S&P quarterly returns, and then stock returns. So one thing we were just curious about was, could we make this relationship from time to log price to book ratio? Can we remove it? Can we make it stationary? Can we do some type of normalization? And so what we found was that if we normalize by the mean standard deviation of this quantity per quarter, we end up with something that's stationary now. And the reason we thought this is kind of a valid normalization or even move to do is that generally most investment strategies is based off the relative ordering of this quantity, not so much the absolute value of it. And so this normalization simply is just trying to remove any possible sector-specific moves that's happening in the market, basically. Now, if you look at the time series graph, we see two more things. One, at least from this algorithm, we see that the previous price to book ratio seems to cause next quarter returns. And also, interestingly, at least to us, that the stock returns is mostly stationary, given the contemporaneous S&P returns and the previous book to ratio. Why mostly stationary? I mean, there is still that black edge from T to the stock returns. But, you know, again, depending on if you buy our argument of lowering the p-value, it would remove it. This observation we think is actually quite interesting and fascinating because long-short portfolios, the intention of it is to remove the effect of like basically the market. So you could say that's being proxied to the S&P returns here. And doing that basically would lead you with something that is more stationary, at least justifying the idea of trying to do this type of investment strategy. Looking a little bit deeper into the data itself, on the left, we have a plot, next quarter returns, previous quarter's price to book ratio. The little squares is a 2D histogram, red, more data, purple, less data. And then the black circles are basically the mean returns in each bin. And so one thing we see, and maybe this is a little bit reading into the weeds, but like we see a small trend between these black dots. And then if you do a standard back test, long only using a threshold, we do see that it does perform better than a market cap weighted portfolio. The black line, importantly, is not the S&P returns. It is the market cap weighted portfolio of this universe specifically that we're looking at. We figured that would make it a little bit more fair of a comparison. The other thing that we noticed, and that might be interesting, is just this correlation with the volatility, that you can see that lower price to book ratio correlates with higher volatility and vice versa. We haven't looked into if there's like a volatility play to be made based off this, but something to point out. And maybe also worth noting that, you know, when in all our graphs, when we said A causes B, it's not simply saying that, oh, if A changes, the mean of B will change, right? This is also a valid clause, right? If you change one variable, price to book ratio, it changes the volatility. This is also going to be captured in our graphs and in our algorithm. Cool. So to summarize and conclude, our main findings. Apple's factor exposures are non-stationary, i.e. time dependent. More that we found this via the graphs. From our experiments, we see it seems momentum causes the HML value factor. And again, this seems to be a causal relationship between price to book ratio and next quarter returns. From a more practical perspective, for people who are thinking about using causal discovery in finance in the real world, or even using our algorithm, you know, our synthetic data experiment suggests the eye test. The choice of it important depending on your data. And I think the weird result that we found is that the linear test of parkour does better with less data, even when the data generating process is nonlinear. Something fun to think about. But again, even more important to us, I think, is the idea of the assumptions, right? If there are assumptions in the causal discovery algorithm, it's important to test it. Is it valid? Does it make sense? You know, financial data, it is non-stationary, has nonlinearity, has lagged and contemporaneous causal effects. And at least, unlike prior work, not to say there won't be other additional work in the future, CD knots is able to handle all these properties. Thank you. Now I guess it's a good time for questions.
Thank you, right on time. And I would like to turn it over to our reviewers to use the raise the hand to get in line for questions. Guido has a hand up. Go ahead, Guido, you're still muted.
Yeah, thanks. This is very interesting. I really enjoyed the presentation. I kind of do have some questions that are at the conceptual level, sort of primarily about the sense in which this is really causal rather than predictive, and kind of how you want to measure ultimately the success of this type of modeling strategy. So suppose I had a different algorithm for kind of discovering the structure here, and it led to a portfolio building strategy that was more profitable. Would you view that in the end kind of as a preferred model? Is that kind of how you would measure the success of one modeling strategy here versus the other? And sort of, you know, one aspect is that one of the last few slides you made the comment that the price book ratio was a causal factor for the returns, and I'm still not quite sure how I should interpret that. And kind of the final question is, let me just get all three of them out. So in some sense, the strategy here relies on the assumption that there's a lot of strong relations between these variables that you can uncover, and then there's a lot of hard zeros, or at least relations that are very close to zero. And that may be plausible in some settings, kind of in sort of in medicine. You could well imagine that particular medication just really has no effect on some illnesses or some conditions. But in social sciences and in finance as well, I would expect that in the end, all these variables have some effect on future values of other things. These effects may be small, they may be big, but in some sense, the testing strategy of looking just for the strong relations and separating them out from the zeros relies on the true distribution of these relations, kind of having the structure that there's a lot of things very close to zero and then some really big things, as opposed to a more smooth distribution where you might want to do kind of rich regression type shrinkage things that leave all the relations there. Let me stop here.
I'll go through this maybe backwards in the order that you asked it, just because the last one is more fresh in my mind. I guess in my mind, the way I look at the idea of removing the edges is not so much a assumption. It is a little bit of an assumption of a lack of maybe saying there are a lot of zeros, but I prefer thinking of it as we just don't have enough data to say otherwise in a statistically significant way. And at least if we are forcing ourselves to have to learn something from purely just data and not through interventions, it is, at least in my mind, safer to just see what the data, or at least if you have the statistics to agree with your claim. I think it's why it's important to also then, be able to make sure you have an algorithm that can allow for longer time ranges, so that way you can actually, again, pull together all the data to actually do it. Of course, there could be just prior knowledge that says that we know A causes B, and the strength is just too weak for us to measure it, but we think it's there. But I think the fact that you would have to kind of almost, it's like an override. It's not to say that the data says it, it's just to say that I know this to be true and it might just be hard to prove it. That's kind of my view, I guess, on the existence and non-existence of an edge. Going to the other question about, okay, predictive versus causal. So I guess the way I kind of think about it is that if you have a causal model, if you have a structure that's supposed to be compatible with the data, then it should be as predictive as any other model that does not go the approach of trying to construct a graph in that way using the same set of variables, right? If it is a true descriptor of the world, then doing some type of Bayesian inference to create a prediction shouldn't be better or worse than taking, or maybe even better, but shouldn't be worse than taking a fully predictive approach. But that in no way means that graph is, but of course there could be multiple graphs that give you the same exact performance, right? And so, because maybe the bias of better prediction is not coming from the fact that there's a causal relationship, it might just be that anti-causal relationships are easier to predict. And so that's why it got better, right? So that's what I think, to a large extent, while we have those examples where we can try doing some prediction, where we can try acting on the graph, I still do believe without interventional studies or randomized controlled trials, it does rest upon the assumptions. And that's kind of one of the best things you can do to justify if you're willing to interpret what you see as causal or not.
Yeah,
hopefully that answers the question.
So actually, just one more comment. Kind of funny thing was that I was actually teaching causal discovery in my PhD class yesterday, so the timing was very good for your guys' presentation. Thanks.
Thanks.
Okay, then I would like to turn the microphone over to Miguel, who is on our review committee. Miguel.
Thank you, Horst, and thank you for the presentation. I have a couple of questions that go in a similar direction about how well the causal structure is being recovered as opposed to finding the correlation structure. So can you help me out with two things? One is that you are making the assumption that there are no unmeasured common causes of any variables. That seems a very strong assumption. It assumes that you know how the world works. Essentially, you know there is nothing that you know that should be on the causal graph. So, my question is: do you have any ideas about how you could go about? I mean, not testing that assumption, which is impossible, but finding evidence that could help prove or disprove it. That is one question. And the other question is, when you use a causal graph with or a causal DAG with the time varying variables, there seems to be these discrete times t. And at those times t, several variables are measured simultaneously. Apparently, this is part of my question, actually. They seem to be measured at exactly the same time. And how does the algorithm handles that? Is it possible that variables at the same time cause each other if they happen really at the same time, or they can only cause by variables in the past, but then what if the interval is very long and there's something happening in the middle? So how does the algorithm deal with those issues? Thank you.
Okay.
So,
Uh,
what do you want?
If you want to take the contemporaneous one, you can take that.
Yes.
And then we go take the other question after.
So in regards to the contemporaneous effects, I would say that our algorithm does handle it. But maybe I should go back and see, we should see why these effects are actually contemporaneous. In a lot of fields, let's say in finance, the propagation of this causal interaction is extremely fast. They can go in a matter of seconds. Fed announce something, in few seconds, all the market's gonna move. So the way we sample this data is normally at a much lower frequency, like we collect end of the day data. So what happens here that we are missing this causal interaction. If we had collected the data in a microsecond, we would have seen that first, like equity move, then bond market move, fixed income move. But since we do it at lower frequency, they're gonna appear to us as a contemporaneous effect. So that's why I was, when I was talking about the causal discovery in time series thing, I was mentioning that we need to be able to handle these cases because this is the case a lot of time we don't collect the data that frequent. So yes, our algorithm does handle contemporaneous ones. A lot of algorithms, except those Granger-based based methods that inherently they cannot handle contemporaneous ones. A lot of modern puzzle discovery algorithms do handle contemporaneous ones, like ours.
And I think to add to that, I guess it's not wrong to think of like contemporaneous effects as like an artifact of subsampling, right? It is like if we truly believe that there's no idea of really contemporaneous effects, that there needs to be a time lag, which I don't think is the worst assumption to make. The fact that we get it is pure. The fact that we have to handle it is just an artifact of the fact that we don't have like we're not working on like microsecond data, right? We're working at daily. To your other question about unobserved confounding. I guess the few thoughts I have along that realm is that there is some work I know, haven't gone too deep into that literature on how to apply causal discovery when you don't want to make that assumption. I think the other approach that makes me comfortable at least is that I guess it's implying that it exists. Or a new technique that would be useful, I think, is again a different type of sensitivity analysis, right? If we could say that what if we believe that up to 10% of the correlations that we observe could be from unobserved confounding? How might that impact what you learn from the graph or the possible solutions? What if you're going to assume 20%, 30%, et cetera, right? I think like I kind of goes to the idea of like the assumptions where it's been bucketed into those three ideas. And ideally, nothing should be in that last subjective assumptions realm, right? In the ideal world, you could move it all at least into like a robustness check. But yeah, I do think that, like the data is just one very narrow perspective almost of the real world. And the only way to interpret it in any causal way just requires always assumptions. And then, and like basically some level of building your own trust that the conclusions you've made are meaningful, it's not overfit, quote unquote, it's not, et cetera. And that's kind of how I think about this problem.
And maybe I add one more thing to it. The assumptions that we use is actually pseudo-sufficiency. So
yeah,
we still can handle some unobserved confounder as long as they can be captured and they change through time, through U variables. But yes, we don't claim that it can capture everything. Yeah, that's the problem in causal discovery.
Yeah, for now.
Thank you.
Thank you. And we have one more question from Pankaj.
Thank you for the wonderful presentation. One thing I would like to talk that if we look at the whole philosophy of causality, Simpson's paradox is quite dominant because that is at the very foundation of this whole causal philosophy. And I see some of the instances where Simpson's paradox can be very vital for your presentation. Say, for example, the way, and that could be very important for black swan kind of event. So first thing is that you talked about missing confounder, and that could be very important factor for Simpson's paradox. Then you talked about p values where p hacking can be very crucial. Then you also talked about backtesting data and data sampling and all those kind of things. And you know that even data sampling can have a huge role in Simpson's paradox. So how do you address the entire thing from Simpson's paradox perspective of the whole thing?
So often when people talk about Simpson's paradox, they're talking about it from the perspective of you have other observed variables for which you can condition on, and then your inference changes. I would say that from an inference perspective, we haven't gone down that realm yet, which is though something that we would love to do next, as once you have a graph, inference should be done. But I think Simpson's paradox is more, I'm not sure if it's a, I don't know if I would say it's not a factor in the discovery component. It's just more a part, like it's more trying to find the confounders. And again, trying to say, is it valid to interpret these as confounders given different statistical tests? And if your graph is fully connected, right? Like say it is X causes Y with Z confounding the two of them, that graph cannot, like orienting those edges cannot be done unless you make significant other assumptions, right? And so that if you want to say, you can interpret that as saying, due to the fact of like some form of Simpson's paradox there, you can't actually orient the edges without other information, without other variables trying to help you. So I guess there's that one. Going off the lines of p hacking, I think that's it was actually something we were talking about actually a few days ago about that might be something asked, that I think this is kind of the example of, again, of like robustness checks and doing a sufficient amount of experiments in your paper to basically create trust in your readers that you haven't hacked your solution, right? But I think, as I put it, like p hacking is stylistically no different than in the machine learning community when you can try to overfit to the task set, right? It is just, there's always this level of, you can always, let's call it hack or lie your way in a paper to get better results. And of course, the two solutions there is either A, trying to reproduce the results, or B, writing in such a way where you've done a sufficient number of experiments and explained them in detail enough that you can at least convince readers that you might not have done that, right? And maybe the solution there is just more guidelines, right? That if you are doing a causal discovery algorithm, if you're going to write a paper applying it to data, to real data, you should show A, B, and C. Like if you show these things, at least it can give better confidence in your readers that you haven't cherry-picked a result. But I would imagine every time, the usual joke, the more metrics every time you come up with a metric, people will find a way to hack it, so there's always this kind of little adversarial game happening. Hopefully that kind of answers your question.
Thank you.
Okay, thank you. So Guido, you still have a hand up. Do you have another question?
Sorry, no, my bad.
Okay. Good. I think then we have reached the end of the questions. So I'd like to thank our speakers for their presentation and for their paper. And I'd like to thank our reviewers for their attention and their evaluations. Don't forget to fill out your spreadsheet. And then I would like to, of course, thank our audience, our global audience, for providing the backdrop for our contestants for the Best Paper Award. So thanks, everybody, and have a good evening or good afternoon or good morning. And I'd like to ask our reviewers and board members to stay on for the next meeting that we still have coming up. Thanks.